Thank you everyone. And my topic is from OOP principle to scalable machine learning system. Have you ever heard about OOP? Please raise your hand. Oh, good. Yeah, everyone knows OOP. Yeah, it's a kind of programming principle. Yeah. So we usually use OOP as programming, not architect. So now I'm trying to port in the programming principle into architecture principle. Yeah. So that's my talk. Okay, self-introduction about me. Yeah, Taiwan. Yeah, small island. Yeah, far away from here. And I like eat food, and I like anime. And I like system architecture a lot. And I'm also a Python Taiwan speaker this year and next year. Okay, so why do I want to do this topic? Before I work in a data science company and we do machine learning system. Yeah, we provide an automatic machine learning engine to our customer, and they don't need to know anything about machine learning. They just need to choose their features and choose their target, and they can run various models. And we will do model selection for them and do hyperparameter optimization. Yeah. So in this case, we have to figure out how our system to be solid. Yeah. So that's the motivation of the topic. Anyone know about Google's rules of machine learning? Wow, good. Yeah, that's a good article from Google. And Google teaches us that how do you build a machine learning system. So they say one thing is about most of the problem you face on the machine learning problem. Yeah, it's not a mathematical problem, it's engineering problem. So they provide 4 principles. The first one is make sure your pipeline is solid and end-to-end. That means from your data source to your model, each stage you should be solid. You cannot, your system cannot be crashed even some of the model is done. So this is important. So it is the first one. And the second one is start with a reasonable objective. In machine learning problem, we should specify our problem well. That's because you cannot say, wow, I want to predict the sales price, and what's your objective? I think accuracy, maybe. Yeah. So that kind of objective, you should specify more. You can just say roughly like, oh, I want to earn a lot in the future. What do you mean a lot? Or I want to have a high accuracy. And what's your accuracy mean? Yeah. So that's very important for machine learning problem. And the third one is you can add common sense features into your machine learning model. That means some people want to they know statistics more, or they know mathematics more, so they are trying to add a very complicated feature into their model. But actually, you should add a very simple feature or common sense features into your model. Something like if we want to predict a sales price of a house, and you can easily to add something like location or weather or the size of your house. And that's common sense. So you should add these features first. Okay, and the next one. Next one is make sure that your pipeline stays solid. Yeah, it looks strange, right? That is the same as the first one. Yeah, so that means this is very important. So Google said twice. So the point of the rules of machine learning from Google is only one thing: solid. Yeah. So let's start. What's the requirements of the machine learning system? The first one is scalability. Yeah, just as a topic of this talk, we want to make our system scalable, and we can easily to add more algorithms into the system. The second one is distributed. if we want to add more models into our system, and we should make our system distributed so that the computing power is strong enough. We don't need to use a single computer to compute all of the models. And the third one is supervise. To become a solid system, we should make supervised mechanism to build a system. So these three combine to solid system. Okay. And what's the implementation of this system? Okay. For scalability part, anyone heard of RapidMiner before? Yeah, they don't. Yeah, RapidMiner is a tool to make you easily to build your data science flow. Yeah, so it looks like this one. You can easily drag and drop your node and build your own data science flow. Something like you want the data source here. Yeah, you want the data source here, and you want to select some attributes and do something here, and do a normalize or something. Increase your dimension, decrease your dimension, something like this, and do cross validation and apply your model to predict the answer. Yeah, that's very easy for us to build our own data science flow. So what's that mean? They use this kind of concept. Linked list is a concept from computer science, and with this concept, you can easily to drag all the process into another process, and you can also add node easily into one process. Okay, so this is a configuration in RapidMiner. You will see there's a process here. Yeah, process here. It contains operator and connect. Operator means the node here. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, 11 operators. And connect means the line between operators. So this is a line, and this we call connect in the RapidMiner. Okay, so for scalability part, we use RapidMiner's concept, only concept. RapidMiner is built in Java, and we want to rebuild it in Python. Yeah. Okay, so for distributed part and supervised part, we use S.O.L.I.D. And S.O.L.I.D is a tool for job delivery, and it can handle job well when you deliver your task. So there are 4 good things why I chose S.O.L.I.D. The first one is zero configuration. Yeah, it's very easy to use. You just import and use. Yeah. And the second one is fault tolerance. In S.O.L.I.D, there are a good mechanism that you can handle all of the errors when your job fails. So you don't need to worry about if some worker died and how can I do? The S.O.L.I.D do for you. The third one is message passing. S.O.L.I.D use the publish and producer and consumer mechanism in the S.O.L.I.D. So they pass the message instead of all. It's just a busy, and I think it's hard to describe. But message passing is a good mechanism. Yeah, and the last one is high capacity. In S.O.L.I.D, you don't need to stuck on a single tool. Something like you can change your RabbitMQ or Redis. You can change what you want for S.O.L.I.D worker. Okay, so let's introduce more about S.O.L.I.D. There's a producer in S.O.L.I.D, and this is a role you have to deliver your task. And here is the queue and the worker. That is RabbitMQ now, but you can change it to Redis or Kafka or something, what you want. Yeah. So it is separated into multiple queues. So you can separate your task into different queues. Let me take an example for you. In our case, we separate into 3 queues. One is for GPU queue, and one is for multi-core CPU queue, and one is for single-core CPU queues. Why do we separate into these 3 queues? That's because For some algorithm, it can run on GPU, and for some algorithm, it can only run on single core. So we want to do a better resource management. So we separate our task into 3 kinds of queues. Okay, so there are consumers in salary, and you just handle the queue, they listen. Yeah, and they finish the job, and they will save the model into the result backend. I think this cache is not a good word. It should be like a storage or a database. Okay, so let's come to the architecture part. And this is the architecture of the whole system. Yeah, it looks messy, but yeah, we can describe slowly about this architecture. For our application, we have a web server interface, and we have an application server to handle the requests. So for web server, we only show the interface of our system. Yeah, like a user can click and do model. And the API server handle this request and translate into the task. So the API server means the producer role in salary. Like here. Yeah, that's the API server. And this queue, we use Redis queue because the official suggestion is Redis queue. Yeah, and we used Redis before, and Redis has some problems because it's still in experiment level. Okay, and for this worker, it is distributed. You can deploy it into several physical machines. Yeah, and in our case, we deploy about 20 or 30 physical machines to handle all the requests. And some physical machines contains GPU and some contains some not. And for the CPU machines, and they only receive the queue, which is GPU queue. Yeah. Okay, so after the worker finish the task, these two means the result backend in this row here. Yeah. So there are database here and storage here. In our case, we save our model into HDFS storage. Yeah, because model sometimes is big and we need to back up the model too. So we save our model into a storage part. And we store our record and the scores, our metrics into a resource backend here. Yeah. So our dashboard can see the performance of our model or the information of our model from MongoDB. Yeah. So for this slide is it's not about machine learning system. Yeah, it's only about the user experience. Because in the dashboard, after you click, you want to click adding a model, and you don't want to refresh the page yourself, right? You don't want to keep refreshing, and that's so stupid. So for this line, we do a pop-up system to with the WebSocket and to do auto refresh for the website. Yeah. So it's not about machine learning, just a basic implementation on web application. Yeah. So let's see architecture of the system. Okay. So the most important part I have described is about S.O.L.I.D. Yeah, that's why Google said it is important. So in OOP, maybe some people remember it. Yeah, but in OOP there is a S.O.L.I.D. This term in OOP. What S.O.L.I.D is the first word, the first lecture. S means single responsibility principle. That means for each node or each class, we should do their own thing. They don't need to do more things. Yeah, that's in programming. So how do we use that in architecture? Yeah. So the first one is operator structure. Yeah, operator is the node we just described before. Yeah, here. Yeah, these are operators. And for operators, linear regression or decision forest, decision tree or random forest, or the operator do something like select attributes or dimension decrease. Yeah, something like this. And this is an operator. So we do all the operators and to build this UML diagram. So there are around 30 or 40 operators we build. Yeah. And the second one is OpenClosed principle. In programming, we often do this with private, protected, or public, this kind of thinking. So how about in architecture? In architecture, the most important part is open for extension, closed for multiplication. So in architecture part, we use process structure. Something like you can it is open to extend your process with connect and operator, and it is closed to multiply because only the owner can modify the implementation of each operator. Okay, so let's see an example for OpenClosed principle. If we want to add one more operator into the process, you can just simply like this. This is a connect from ready CSV to reset default type. If we want to do something like a dimension transform before resetting the type, you can just connect the read CSV into dimension transform, and then you can add one more connect to another operator. Yeah. Let's say a simple example. And for the third one is this called substitution principle. That means for each operator, you should be able to substitute the parent operator. So there are 4 things we have to follow. It's too long to read. That means for your children, you should be able to substitute your parent. Something like this. You can see the code. This is I can see well, but this neural network is a kind of supervised. Yeah, it's a kind of supervised model. So the attributes in neural network should be contained. Should be contained in the supervised model. Yeah. And for interface segregation principle is this is more programming part. Yeah, because that means you only do the things you want. Don't do all the things by inheritance. So in scikit-learn, maybe someone used scikit-learn before, and in scikit-learn there's a lot of missing function in scikit-learn. So something like transformer missing or linear regression missing. Yeah, there are lots of missing in scikit-learn. So we apply this principle into our system. Like a label encoder, we don't need to predict. We only need to transform. So we just mix transformer missing into the code. Yeah, the next one is dependency inversion principle. That is hard to describe. That means your children cannot depend on. You should depend on interface. You don't need to depend on the instance. So I just give a bad example. I found this while preparing this talk. Yeah, but I have no time to fix it. This means there's a unsupervised model, and you can see in apply function we call a function predict, but there's no interface called predict. Let's try. I think that's a bad point in Python because Python won't do that kind of checking for you. Maybe I don't know. So I missed this. I made this mistake before. So that's a bad example, not a good process. Okay. So I think the most important part to share with all of you is the troubles we have made. And actually now we didn't use this system. We reflect all of the system into Scala. So I will introduce the troubles about this one. Okay. The first one is operator implementation. Yeah, maybe someone is. I want to ask a question about operator implementation. There are several methods. Like the first one is we can implement with class, and the second one is we can implement with function. So just think about it. If we have to implement this operator, so you will choose class. Please raise your hand. You will choose class to implement operator. Please raise your hand. No. Really? Oh. And if we want to, if you will implement this operator with function, raise your hand. Okay. So I thought the other people will use, ask others to implement. Yeah, not implement themselves. Yeah. Okay. So yeah, we try all the methods. The first one we try is class. Yeah, class seems makes sense. Yeah, it really makes sense because it's OOP, wow, OOP you can inherit and you can do well. But we found that it is stable. Yeah, so for testing, for debugging, and for parallel, it is not a good way to do that. Yeah, so we change all of our codes into functional. Yeah, so we build all the operators into functions. And we think, wow, so good. Yeah, it's easy to test and it can parallel very, very well. Yeah. But we found another one is for a simple operator, we should write a lot. Something like in machine learning, there are lots of linear regression, like ElasticNet or lasso loss. There are lots of algorithms. It's about linear regression, but we should write all of them. Again and again and again. We cannot do any inheritance yet. So we do mix. Yeah. We think that class doesn't work and function doesn't work. And how about mixing together? Maybe it works. Oh yeah, actually it works. Yeah. And how it works is that for inheritance part we will use the class, and for the operation part we will use the function. So it can, it will be static and also be inherited. So let's give an example about this one. Okay, in neural network there are lots of neural network. Yeah. So in here, this one is category. These two. One is convolutional neural network, and one is LRCN. Yeah, it's a kind of neural network. It's similar to LSTM. Yeah. So these two we use the same class, and so we can put all of the basic part into the neural network class. Yeah, something like we use keras. So for keras setting, we put in the class. We put in the class. And for another setting, how many layers in convolutional or the time window for LRCN we put in the function part. Yeah, that's what we do. And the second one is complicated usage. Yeah. As you see before here. Yeah. It is only for one connect and one operator. So you will think about, wow, one connect and one operator. So let's take a look about this one. Wow, if you have 11 operators, and wow, how will your configuration look like? It will look like very, very messy, and yeah, it cannot be developed. So for this part, we think about we should break into sub-process. So let's actually recommend it already. Yeah. So in here, like a cross-validation, you can click into the cross-validation part and see another sub-process. Yeah. So this is a good way if you want to develop this kind of system. You can't only develop a single process. You should make your process can contain another process. Yeah. So let's talk more about process. If you finish setting your configuration like this, yeah, maybe around 100 lines code, and how do you validate? There are two ways to validate. The first one is you can implement your own runtime validator. Something like that. You can check the connecting or check the properties to make sure your process runs well. But yeah, that's a difficult part because we did that before. We always miss lots of cases. We miss lots of cases, so actually we choose another method. Yeah, we just change the language. Yeah, into Scalable. Yeah, it will make the compile time tracking for us and is easier to develop. Yeah, and the difficult part is memory limitation. If you do machine learning job, if you do machine learning in your job, sometimes with Python, sometimes you will face this kind of problem because in most cases we use our single machine like a laptop to run the algorithm. Yeah, so there are two parts you may face for memory limitation. The first one is your data size. If we want to load all of your data into your laptop to process, it will face OOM. That means for pandas, they don't separate into different chunks. You can do chunk processing in pandas, but only on a single laptop. So if we want to do chunk processing means a small batch processing for your data set. Yeah, you can try to use Desk. Desk is a tool that parallel your job into multiple physical machine. Yeah, and the syntax is similar with pandas. So if you are familiar with pandas, and I know you can be, yeah, you can use Desk easily. Okay, and the second one is about computing. Even you load all of your data into a memory, you have to think about the computing part. Yeah, because in machine learning, you need lots of memory to compute. So for scikit-learn, yeah, no parallel. So yeah, actually there is, but it cannot be multiple physical machines. It is very important to separate it into multiple physical machines because, yeah, as I said before, you have to add more algorithm into your system. So if you run all of the things in your single machine, that will be very stupid. Yeah. So this is a suggestion for parallel. And I think the next one is about CPU bounding. Yeah. Actually, there's a problem in salary. Yeah. Salary have to make a profit between worker and producer. So you cannot use all the resource of the machine. You have to keep some for salary for communication. Yeah. So you have to set worker concurrency. That means you don't need to. You can use all of the cores to in your system. You only can use like a n-1. Yeah, you have to keep one core for salary to communicate with other workers and producers. Yeah, do not use all of the cores. Yeah. Okay, so for supervised part, there are a few suggestions about the system. The first one is Flower is a tool to visualize salaries text, but it is an open source, but there's a little, yeah, some suggestion for this software. Flower only updates their interface when text is updated. So this is not good if your text is not updated, but your worker actually died. So you have to think about this one. And for error message part, it's common sense. You have to do readable messaging. So your data scientist will not complain about you. Yeah. Okay. The next part is I faced that I haven't solved it, and it maybe someone can solve it. Yeah. I hope. Yeah. Worker loads means like here we say that CPU bound task will use all of the CPUs for the machine. Even you set the worker concurrency for the salary. Sometimes, not usual. Sometimes your task will run out of your resource, and the salary worker will be died. Yeah, so will be dead. So I haven't finished. I haven't solved this problem yet. Hope someone will fix it. Yeah. So that's all about my talk, and thank you very much. And which version of Celery? I just use the latest stable version, and I don't think, I think there's no difference. Yeah, and I think Celery is a good tool. Yeah, if we want to do test delivery job. Yeah. Wow, cool. No question.
There's one more.
Oh. Oh yeah, the question I just explained. In my case, we set one core for in each visual machine, let Celery to communicate with each other. But even we did that, the resource still ran out sometimes. Not usual, but sometimes the resource ran out. So maybe we should set more. But I don't think it's a good idea. We should take a look more about the resource management part. Yeah. And we'll try setting Celery process. Nice. We have never tried about this one. Maybe we can try in the future. Yeah. Thanks for the suggestion.
I have a question. How long the machine learning process takes? It's hours, days, months?
Around the longest one is around several weeks. Several weeks. And the shortest one is around several minutes. Yeah. And you can set the timeout of the task on Celery. Yeah. The default, I think the default is 1 hour. Yeah. What was? That's a really good question. Yeah, actually, this is the problem we face, and that's why we switch our system into Scalable. Yeah. In this system, the largest one is around 10 gigabytes. Yeah, and more than 10 gigabytes, it will be very, very unstable. Yeah. So, but within 10 gigabytes, it works very well. And actually, there's a transition version in between Python and Scalable. We built a PySpark version. Yeah, and because we thought like, Python, we don't want to store Python, we want to use it more. Yeah, so we use PySpark in a transition version. But because we do the system, we didn't. It's like we have to develop a system, not a solution to something like if we want to calculate the count of the sales price, you can just write a script and send it into a Spark cluster. But in the engine, you cannot do that. It's very hard to handle the errors if you use PySpark. Yeah, but if you do research, you still can use PySpark. But if you do product, I don't think it's a good idea to use PySpark. Yeah. Auto scale work. No, we didn't auto scale the workers, but I think that's because yeah, we didn't do that. But it's a good suggestion, and you can just use Amazon auto scaling group to do that kind of feature. But actually, because our service is on-premise solution, so we cannot auto scale the physical machine. Yeah. From different speed up from different size. For large, for these 4 scales, right? For the small and medium part, I think the easiest way is vertical scale your machine. Yeah, just like you can buy more cores in a single machine. Yeah. And for the third and the last level, for the third level, I think it is. I suggest, in my opinion, yeah, we will do sampling for large data set. But for huge data set, yeah, I think we will do sampling plus clustering. Yeah. But sometimes some algorithm cannot be parallel now. So for that kind of algorithm, we will only do sampling or use GPU to speed up. Yeah.
So it seems there are no more questions.
Yeah. Yeah, thank you very much.